This is a pregnancy test, and I know what you're thinking. No, I'm not pregnant. Yet. In September 2020, I saw this post on Twitter of a programmer playing the 1993 classic video game Doom on a pregnancy test. A little digging into the thread does show that this was a new screen and a new microcontroller not native to the test itself, but it's still wonderfully dumb. There's a long history of people playing Doom on hacked devices not meant to play it. For instance, here's somebody playing Doom on an ATM. Here's somebody playing Doom on a calculator powered by potatoes. Here's Doom running on an ultrasound machine, which continues to beg the question why the Venn diagram of Doom hacking enthusiasts and pregnancy detection technology continues to have such a large overlap. But all this got me thinking, what mark could I leave on this ever-growing list of playable versions of Doom? Well, recently I came across another tweet, this one, in which a user was able to create an animation using only Spinda patterns. And like any sane person, that led me to the question, what if you could play Doom in Pokemon? Oh, sorry, I misspoke. I meant, what if you could play Doom on a Pokemon? Surely deciding to make this video won't send me down an unfathomably deep rabbit hole, which will require me to learn more about Doom, Spinda, and computer science than anyone should ever have to know. Right? Well, given that I'm filming this after having already done all of it, I can tell you pretty much, spoiler alert, this video essentially broke me. Okay, so my first hurdle in getting Doom to run on Spinda was understanding how Spinda patterns worked in the first place. To represent even one frame of Doom, I'm going to need an incredibly specific Spinda pattern, right? But how does the Game Boy Advance even determine which patterns are possible? Like many other people, I first encountered Spinda while playing Pokemon Sapphire version and traversing Route 113. This is my actual childhood copy of Pokemon Sapphire, and I was playing it exactly 10 years after Doom came out. Coincidence? Yes. Almost certainly. As you may already know, every single time you encounter Spinda, the game randomly generates a pattern of 4 dots to cover its face in some configuration. Like any functioning adult, I have a favorite Spinda pattern. Don't you? Of course you do. You're a normal person, like me, that has a normal brain. Okay, which one's yours? You don't? Okay, well this one's mine. This is my favorite.
He's gay, but he has a special connection to classical music. There's many things that are interesting about him.
Isn't it beautiful? I really like how the top left dot is just in like this really... Wait, hang on, what is that? What is that number? What's that number in the bottom? No. I said I wasn't gonna fall down a rabbit hole. No. We're not finding out. Don't transition to a voiceover segment. No VO, no! Every Pokemon has a randomly generated personality value, or PID for short. Personality values are used to store tons of information about a given Pokemon. If they can have more than one ability, the PID determines which one they will have. It also determines whether a Pokemon is shiny or not, the Pokemon's gender, and a few other things. For Spinda specifically, the personality value also determines the locations of each of Spinda's 4 dots. But how does it do this? Well, the personality value is stored in a 32-bit unsigned integer. Good lord, the technical jargon never ends. Okay, let's break it down. First, the word unsigned here just means that we aren't dedicating any part of the number to store whether it's positive or negative. The number is only going to be positive. Next, bits. A bit refers to a digit in base 2 or binary. Let's take a look at that number again. This is hexadecimal, also known as base 16. Here on Earth, we largely count in base 10, otherwise known as decimal. But base 10 isn't the only counting system. Many cultures throughout history used other counting systems, but we likely settled on base 10 for a myriad of reasons, but most probably because it made counting on these things pretty convenient. One thing to note about hex is that since we don't have any unique numerals in our modern writing system above 9, any base higher than 10 starts to use letters of the alphabet for the higher numbers. For instance, an A is 10, a B is 11, on up to F for 15. A place you may have come into contact with hex in your day-to-day life is computer color palettes. If you've ever used Photoshop or MS Paint or really any color swatch in a program, you've probably seen the box for hex and some weird number that has an F or other letters in it. That's hexadecimal. The algorithm that determines a Spinda pattern looks at the hexadecimal number representing Spinda's PID and uses 2 digits at a time to represent the X and Y values respectively for a spot in each quadrant. Given this, that means that the number of possible unique Spinda patterns is equal to the maximum value that you can store in this 8-digit hexadecimal integer. That number comes out to be 4,294,967,295. That's how many bits of memory can be stored in a 32-bit address, and conveniently, also the number of possible Spinda patterns. But even if I wanted to represent a really rudimentary game like Pong, I would still need a ton of unique Spinda patterns to represent every frame of every possible game state. I can't possibly go through the game and catch all those Spinda by hand or even pick out the Spinda patterns by hand. It's just unrealistic. So that meant my next goal, after finding out how Spinda worked, was to create sort of a Spinda database of every single Spinda pattern, and then create a Python program that would pull sort of a Spinda of best fit, if you will, when I gave it an image. Then I could just do that Spinda of best fit comparison for every single frame of a clip of me playing Doom, and bada bing bada boom, we've got Doom running on a Spinda, baby! And better yet, if I could make the program tight enough to run the comparison in real time, we could play Doom in real time on a graphical user interface made out of Spinda. Wow, it feels like I've solved the whole thing. Oh no, there is so much time left on the red scrub bar on the YouTube player. That's weird. I feel like this should be over now. We did it. The first problem I encountered is that I'm stupid. Or at the very least, I just am not talented enough at programming to solve this problem in the amount of time one would call reasonable for a video deadline. The next issue is that as I worked through the problem, I realized two new massive problems. Firstly, the amount of computing power and the elegance of the algorithm that would be required to generate the best Spinda in real time while playing a game is just not anything I could possibly do. I think it might be possible, but not by me. The second problem is that I pretty quickly realized what was probably evident to you almost right away. How do you represent a game as visually complex as Doom using only 4 dots of slightly different size on a canvas only the size of Spinda's face? Not only that, but because the dots are constrained to 4 quadrants with finite boundaries, that means that some images just aren't possible to recreate in a way that feels satisfying. But as I was trying to reason through those problems, I had a bit of a eureka moment, and I think I came up with a solution to the second problem. If one Spinda isn't sufficient, how about basically a matrix of Spinda, in which each individual Spinda, instead of having to recreate the whole image, only has to recreate a small part of the image? Obviously, this is infinitely scalable, and you could just use a really large image and enough Spinda that each Spinda is basically just functioning like a pixel, but that's not really any fun. So I decided that my goal for the project would be able to make up the image using Spinda that are large enough to be visible for each subsection of the image. That way it actually feels like you're looking at Spinda. With that in mind, I got to work. My first idea was to go into Photoshop and just sort of make a mock-up of what I was thinking about. So I took a screenshot of Doom, and then I transitioned it to black and white, and then I filtered out all of the white in the image to reveal a grid of just one Spinda pattern I had made behind it. And before I show this to you, I should make a content warning that it is complete nightmare fuel, so watch at your own risk. Here it is. So after making this monstrosity, I decided that if I just hopped in Python and gave it an earnest effort, hopefully it wouldn't look like that. I started researching algorithms to make mosaics in Python, but with an image database for Spinda being over 4 billion images, and with my programming abilities fast approaching their present limit, I needed a lifeline. I decided to revisit the Spinda animation tweet to see if the original poster had a GitHub link or anything in the replies that might clue me into the method. That's when I saw it. The light I had been looking for in this very dark, Spinda-themed tunnel. A reply to the original tweet showing a series of Spinda being used to animate Bad Apple, which I'm told is a meme about anime? I don't know, man. I've been in a Spinda rabbit hole for so long, I don't really know about anything anymore. But this was a long clip, and at a decently high frame rate, too. This had to have been generated using a program, as no sane person would ever manually pick this many Spinda patterns. I tweeted at this Ovidios person and waited. About 15 minutes later, they DM'd me. Eureka! Oh my god, it's happening. It turns out this legend's name is Jakob. I asked Jakob if he had a Git repository for his Spinda code, and he said he'd happily upload it. Jakob and I wound up talking for quite some time about how I could go about this project using Jakob's code as a jumping off point. But ultimately, Jakob's code proved to be more than sufficient for what we wanted to do. Jakob and I agreed that one Spinda's face was probably not going to be large enough, and I told him about my mosaic idea. I had planned to use his code to start making the mosaic myself, but within one day, I received a DM from him with the following image. Jakob had decided to just code it on his own in his free time because he thought the idea was interesting. Literally saving me so much time, I cannot thank him enough. He sent me the code and we hopped on a call to make sure everything was functioning, and I got to work. I recorded gameplay of Doom at a very low resolution to make sure that I didn't have to use too many Spinda to represent the image, and I recorded it at a low frame rate so that we wouldn't have to process so many images. It was finally time to test out this brand new program that Jakob had written. But first, to understand how the mosaic code works, we need to understand how the simpler version of this program works, the version used for the bad apple animation. Jakob's code is a sort of quick and dirty but very effective solution to the problem of selecting the best Spinda for any individual frame. The code uses a genetic algorithm, which is based on real-life natural selection. Basically, imagine some very selective daycare breeders who are given 2 Spinda and a target image. They breed the Spinda together and a litter of Spinda are made. We'll call this Generation 0. In Generation 0, they look at every Spinda and assign them a score based on how close they are to the target image. This is known as a fitness score. The Spinda with poor scores are sent to go have lovely little lives in the daycare fields. The Spinda with good scores, however, are put to work, baby. They gotta make that next generation of Spinda right now. This process is repeated for a specified amount of generations or until a requisite fitness score is reached. For example, let's say I want to recreate this one specific frame of Bad Apple. The algorithm sees white pixels as parts of the image to recreate with the dots, and black pixels as parts of the image for which to use blank parts of Spinda's face. For the following simulation, I did 100 Spinda per generation and 10 generations. It's obviously not great, but with only 4 red dots to work with, it's really not bad. The general shape of the image is definitely there if you kind of squint a little bit. Increasing the number of members in any given generation, or increasing the number of generations, could help with the simulation a bit, but there's 2 problems with that. First of all, there's only so much we can do when trying to recreate a complex image with only 4 red dots. Getting close to the target image is a little subjective, given that the fitness score will never really be that good. The second and perhaps larger problem is that increasing the number of generations will linearly increase the amount of time it takes to compute, but if you increase the number of members in a generation, you are increasing drastically the number of comparisons that have to be made each time a generation is processed. But all that aside, using Jakob's algorithm, we can simulate Doom on a Spinda's face. We're there, the long-awaited moment. Before we do any of the mosaic stuff, we've accomplished the thing I set out to do at the beginning of this project: play Doom on one single Spinda's face. Also, before I play you the clip, I do want to mention something hilarious, which is that when I went back to that Twitter thread of Spinda animations, it turns out I'm not the only person who, after seeing this animation, had the first thought of, oh, you could probably play Doom on that. So shout out to all the other people who also tweeted that, but I'm the only one actually doing it. So internet points to me, bonus 10 internet points for ADEF. I win. I'm winning. Even though I didn't really program much of the actual stuff that's happening. Anyway, onto the clip. Here's that same low resolution, low frame rate Doom gameplay I've been showing you throughout the entire video. Now let's see what it would look like if a vast majority of the screen is represented by one Spinda's face. In the bottom right, you'll see every single Spinda's personality value represented in hex. Okay, so obviously it's not great, but look, it is an accomplishment of the original goal. Just for kicks and giggles, let's see what it would look like if instead of taking up a vast majority of the image, Spinda were only used just to represent the area around the player's gun. Okay, it's still not better. You know what? It's fine. It's fine. I'm fine. Oh, I'm getting a text and they're asking if I'm fine. I'm totally fine. I'm 100% fine. Guys, I'm fine. You can probably see by now why I knew that we'd need the mosaic thing before even simulating all of this. There just isn't enough resolution on Spinda's face, unfortunately. But in the same way that you can't play Doom with an image of 4 pixels, it's okay because all you have to do is just layer many of those 4 pixel images next to each other and voila, it's readable. The process is the same as before, except the algorithm now breaks up a test image into many sub-images and finds the best Spinda for each sub-image. For example, for this Doom logo, which is 839 by 764 pixels, it comes out to be about 36 Spinda by 36 Spinda. The same genetic algorithm to find the best Spinda for one entire image is run for every single Spinda in this list, which means the bigger the image and the bigger the population size in any given generation, the longer the runtime. These simulations can take a while. This Doom title screen image alone took my computer over an hour. But if you're willing to dedicate the computational power and time, amazing things can be achieved. I present to you now Jakob and I's magnum opus. What you're about to see is the same Doom footage as before, but this time processed through the mosaic version of the spindification genetic algorithm. Please enjoy. Isn't it awesome? Now, this code can likely be improved. I mean, for God's sake, you've probably noticed that this clip is only like 10 seconds long. That's because of the sheer amount of time it takes to simulate these frames. Jakob and I split up the rendering task with him taking the even frames and me taking the odd frames, and even then, we still spent dozens of hours of computation time on this 10-second clip at 20 frames per second. We basically just let our computers run on this program whenever we were out of our respective apartments or just didn't have any computer work to do at the time, and it still took so long. Meanwhile, racking up both of our power bills for the month of April. LOL, join the Patreon, link in the description. And there are almost certainly other solutions out there to this problem, many of which would probably be faster to simulate. So, dear viewer, I leave the optimization or complete redesign and overhaul of this solution to you as basically voluntary homework. If you watched this video and thought, I bet I could write a better version of that code, then please, I encourage you to try. This is a really engaging problem and causes you to come up with some very unique solutions. I'll link Jakob's GitHub, including the Spindify page, in the description below, so take a peek at the code, but I'm also gonna link Jakob's website. Jakob is an actual, literal legend for helping me so much with this project, and I cannot thank him enough. I also think Jakob would probably want me to emphasize to you that this is not code that he has taken a lot of time to optimize or make a ton of deeper and deeper solutions to, because after all, neither Jakob nor I have the time in our day-to-day lives to dedicate to this one problem, but the code exists, is functional, and you should definitely try it. As the code is written right now, it worked amazing for this project, and again, thank you, Jakob, so much. Woo! This video turned out to be way bigger of an undertaking than I had thought it was gonna be, which is kind of how all my videos go. So please consider subscribing and liking the video, it really does help. Also, I have a Patreon. This is the list of top tier supporters who are supporting the Patreon right now. Thank you so much to all these patrons. If you want to support me on Patreon, the link is in the top of the description. It really genuinely helps. I could not do this without them. All right, gamers, thank you so much for watching, and I'll see you next time.